electrophile, but from the nucleophile towards the benzene ring. Okay? And that puts a negative charge in this ring, and so here it is. Okay? That negative charge is an allylic anion, so it puts a negative charge here, and when it's sitting here, you notice it can delocalize into the nitro group, and that gives you an additional resonance structure that is makes the system quite happy. Or you move the negative charge over to this ortho position, and there's a second nitro group. This would work with just one nitro group, but I've added two. I made an example with two of them. The additional resonance structure is here. So the negative charge is reasonably happy. Overall, of course, the system is not as happy as where it started. In other words, it's a higher energy. These are all higher energy structures because you're destroying the resonance, the benzene aromaticity. You still have resonance, but it's not aromatic resonance, which is an extra stabilizing force. And so, not surprisingly, the negative charge comes back and kicks out the leaving group to regenerate the aromatic benzene ring. So that's the driving force of all of this. That in the end, the chloride has been replaced by the nucleophile. So we can look at the movie of that. Oops. So here's the chlorodinitrobenzene. And here comes the OH, and we look at this molecular model. You can see this is a flat and sp2 hybridized carbon. And then it attacks, and notice what happens. This carbon now becomes sp3 hybridized, very much like electrophilic aromatic substitution, but the backbone now contains a negative charge. Okay? And in this structure, we've already pushed the negative charge that develops here into the nitro group. Okay? So just showing the particularly stabilizing resonance into the nitro. And then the electron pair comes back and kicks out the leaving group, and that's all there's to it. So this works, but of course it's limited. It only works if you have at least one, ideally several electron withdrawing groups on the ring. Best if they're resonance withdrawing, but several trifluoromethyl groups, for example, sitting on the ring, will also enable the nucleophilic aromatic substitution of a leaving group. These groups do not have to, if they're resonance accepting like nitro, do not necessarily have to be ortho or para. They could be meta, but then you need to beat on the system much harder. So then it's just an inductive effect that this nitro group exerts to stabilize the negative charge, because the negative charge will bypass the carbon that bears the nitro group. So best is either ortho or para or both, and as many as possible, resonance accepting substituents like nitro, carbonyl, nitrile, sulfonyl, and so on. Then you can do this at the room temperature sometimes to do the substitution. But again, it's limited by the fact that your substrates have to bear these groups. Okay, so here's case 2, which is sort of a curiosity, although in the last 10 years people have developed some synthetic chemistry coming out of this. And it originates from the observation that a reaction that wasn't supposed to proceed did proceed as long as you really beat either beat the living daylight out of the system, in the case of the poor nucleophile water, or you use an extremely strong nucleophile, namely amide. Then you can do it at lower temperatures. So up here is the example where people found that chlorobenzene, when you heat it up with sodium hydroxide, aqueous sodium hydroxide, and you have to go to over 300 degrees, and this builds up pressure of about 150 atmospheres in a pressure bomb, and you beat on it like that, and then work it up with acidic water, you get phenol. And this was actually, for a while, used industrially to make phenol from chlorobenzene, because chlorbenzene can be made simply by chlorination of benzene. And chlorine is cheap, benzene is cheap, and so this used to be a viable way of making phenol on a fairly large scale. And these conditions are palatable if you're making a lot of money, but you have to build special equipment. Clearly, this is not something one would do in a research laboratory. Okay? Similarly, if you use a very, very strong nucleophile, amide is an extremely strong nucleophile. Remember, the pKa of ammonia is about 33, so the anion is extremely basic, but it's a small nitrogen-bearing anion that is also extremely nucleophilic. And so with this guy, in liquid ammonia, even in the liquid ammonia temperature, which is minus 33 degrees, that's the boiling point of liquid ammonia, you get displacement of the chloride. Okay? And so for a long time, this was puzzling, because this isn't supposed to happen. And people wondered how this really goes. Until a clever chemist, whose name is Huysken in Munich, decided to do a labeling experiment where he labeled the carbon that was bearing the chlorine with C14. Okay? And he did the experiment with potassium amide. And if there is some kind of direct substitution on this carbon by the amide somehow adding and then eliminating, perhaps by nucleophilic additional elimination, then of course the only product you should get is this guy here, which bears the label at the carbon that bears the amino group. Okay? But he found that this was only half of the product. The other half was a product where the amino group wound up next to the label. Okay? And this was a clear indication that there was an intermediate that equilibrated the two positions, and that the amide would attack that intermediate 50-50 chance, a symmetrical intermediate, 50-50 chance at either carbon. And that led to the postulate that what we're seeing here is the formation of a triple bond. Okay? In other words, the strong base or sodium hydroxide at elevated temperatures affected actually an elimination of HCl to make the triple bond. Not unlike, at least topologically, the E2 elimination of an alkenyl halide to make an alkyne. That was a method that we used to make alkynes. We used to brominate a double bond to get the dibromoalkane, and then eliminate once, gives you the bromoalkene, and then eliminate again, or haloalkene, eliminate again to put in the triple bond. So formally, this is exactly what happens here. And there are two resonance structures that you can write, either the alkyne resonance form, or this guy here that you get by moving the 6-electron pi system of benzene around. This one is called a cumulene type resonance. Turns out, from isolation of benzene at liquid nitrogen temperatures, and look at the spectroscopy and the like, it looks like this is the major contributor to the resonance structure. It's a triple bond in the 6-membered ring. Of course, that's terrible, okay? Because the triple bond wants to be linear. So it's forced to bend back to allow this carbon frame to exist. And if you look at that orbital picture, there is, of course, the normal benzene pi frame. This is now looking at the top, so you're seeing the top lobes of the p orbitals as you go around the ring, and the back lobes are sort of added at the back here. And then perpendicular to that is the second pi bond of the triple bond. Okay? And so it's two p orbitals that are perpendicular to the pi frame of the benzene ring. They're not interacting with that pi frame. And because you're bending back these carbons, the hybridization at these carbons can't be proper sp. And so they're sort of in between sp and sp2, meaning that you have a lot of sp2 characters still in these orbitals, and they're pointing, rather than pointing, as in alkynes, the arrangement is parallel to each other, they're pointing away from each other, and therefore this overlap is poor, and therefore the second pi bond in this benzyne intermediate is terrible bond, very weak bond, imparting a lot of reactivity, diradical character, as people call it colloquially, on this bond, and that makes it extremely reactive. And this is why this works. So mechanistically what happens is it eliminates, and the elimination, because the benzyne, that triple bond is so terrible, actually does not follow an E2 mechanism, meaning that proton and leaving group, proton is abstracted at the same time as leaving group is leaving. It's stepwise. It first deprotonates to make the phenylamine. Okay? Notice this phenylamine has an electron pair and a negative charge sitting in an sp2 orbital that's perpendicular to the pi frame of the benzene ring. It does not interact with that pi frame. Okay? So these double bonds are unperturbed by the fact that you're making a negative charge. And then once the full negative charge is developed here, then it swings around and kicks out the leaving group to make this half-assed triple bond that we've looked at just a second ago. And this guy is so reactive that amit traps it to make the product. Notice, however, the important part is that after elimination, this species is symmetrical. The only difference is in Huysken's experiment was that the top guy is C14, the bottom is carbon. But chemically, the two are essentially indistinguishable. And so amit attacks this guy now, either from the top or from the bottom, to make either one of these new anions. So, and then this anion removes proton, and you get the product. And you notice with the label is now scrambled over the two positions. And so this is how that one goes. So here again, amit approaches and removes this proton. And notice it's not concerted, so it's not proton removal and leaving group leaving at the same time. And then the anion kicks out the chloride. This is a little bit reminiscent, that some of you may have noticed that, of the dehydration step in the aldol condensation. After the aldol addition, remember we make a new enolate. We have to first preform the enolate, and then the enolate, the negative charge comes in and kicks out hydroxide. This was because hydroxide is such a lousy leaving group, and it's not going to leave until there's a full negative charge next door to kick it out. Okay? Unlike an E2, where just a little bit of a buildup of a negative charge induces the leaving group to leave at the same time as the proton comes on. Yeah. In hydroxide. And that's obviously a terrible reaction because the phenylamine, the pKa of phenylamine is about 44. I think I even gave the number up there. So that's in the regime of an allylic CH bond. So to pull off the hydroxide from an allylic bond is also terrible. You can't do it under normal conditions. That's why they use 350 degrees to be able to pull that off, literally. And so here's the benzyne, and it's symmetrical, and now you can approach this from it's trapped by the amit, and that makes the carbon-nitrogen bond, and then the phenylamine, of course, it's highly basic, just exchanges back to and so all this is in equilibrium up there, and then it sinks into the product. So these are all very high energy intermediates. Synthetically, obviously limited. It's a curiosity in that sense. One can make benzynes, however, by other means. For example, you can make benzynes from orthodibromobenzene treatment with lithium or magnesium, makes the monogrignard, and then that generates a negative charge next to the leaving group, and it makes magnesium bromide in the triple bond as a highly reactive intermediate. So you have to make that in the presence of a trapping agent. So benzynes have, for example, started to find use in Diels-Alder chemistry. We generate the benzyne in situ as a reactive intermediate in the presence of a diene that traps the triple bond. So that would be a potential application, but we won't go in that direction. Nature clearly does not look at this that way. And so here we are back to something some more familiar ground, which actually has some great utility. In fact, for over 100 years, this has been used. This was the staple of synthetic organic chemistry to generate substituted benzenes that were substituted by nucleophiles, including phenols. And that is based on turning the amino group into the corresponding diazonium cation, which we did last Tuesday. And in the case of aryl diazonium, these guys are stable. And the reason that they're stable is there is resonance that you can see here. One can delocalize that double bond into the electron-withdrawing nitrogen up there. And perhaps more importantly, the N2, when it leaves, will generate a phenylcation, which makes a positively charged sp2 hybridized carbon, where the positive charge is in an orbital that, again, is perpendicular to the pi frame. It's not stabilized. It's very unhappy. So because when the nitrogen leaves, it would leave behind something extremely unhappy, much more unhappy than a primary alkyl cation. It hangs on for a while. Or, looking at it the other way around, the carbon hangs on to the nitrogen because it doesn't want to become positively charged. Okay? But when you increase the temperature, this is at room temperature, when you go to 50 to 80 degrees, the nitrogen blows off. You get phenylcation, which is immediately trapped by water to make the corresponding phenol. And so the mechanism that we briefly looked at on Tuesday, we'll do again here. So remember that this is a reaction of primary amines with the nitrosyl cation. And so you start with nitrous acid, typically derived from sodium nitrite, so the sodium salt of this nitrous acid. And you add sufficiently strong acid that you get protonation to turn the OH into a good leaving group. And then the leaving group leaves, and you get the nitrosyl cation, which is resonance stabilized, very much like the nitronium that we saw in electrophilic aromatic substitution with nitric acid. Okay? And then this guy is less electrophilic than nitronium, but still a strong electrophile. It's after all positively charged, and it will hit the amino group of aniline, of benzenamine. And so this can be written, well, let's go do it here on this resonance form. And this gives you the first step of the nitrosation. and a positive charge now on this nitrogen. So now the electron pair comes back, proton is lost, and you get the N-nitroso compound. Okay? In the case of a disubstituted nitrogen, so if you have another substituent here, typically alkyl, that's a stable compound. It just sits there. And that was the origin of the N-nitrosamines that we discussed briefly in terms of carcinogenic potential and the controversy associated with them. It's derived from the fact that nitrates and nitrites attack the amino functions in your body, and so people are worried about when this happens. But of course, chemistry happens in your body all the time. Not all of it is bad. So this guy, when it bears a proton, is capable of doing tautomerism, where this proton migrates over to the other side with acid or base. This is done under acid conditions. Remember, we're generating this with acid. And so we are protonating on oxygen and deprotonating on nitrogen. Classic tautomerism mechanism. So we're deprotonating here, which we can write as electron pushing, like that, which gives us an NN double bond. And at this stage, the molecule starts smelling blunt because an NN double bond is 2/3 of the way to an NN triple bond. And under the acidic conditions, you just protonate again and turn that OH into a leaving group now. And the leaving group leaves. And that gives the phenyldiazoniumine, like it's called, which I'll write in the resonance form of a triple bond and then triple bond, but the two resonance forms you can write. In the case of this being alkyl, the N2 leaves instantly. The nitrogen leaves and gives you a primary carbocation. You get a mess. But in the case of phenyl, that thing is sufficiently stable because of a little bit of resonance, as we're seeing on the slide, as well as the fact that when N2 leaves, it leaves behind something that is not very healthy. Namely, when it leaves here, it gives a phenylcation. And again, this phenylcation, this orbital is sp2 hybridized in the plane of the board, whereas the pi frame is perpendicular to the plane of the board. So this is not a resonance stabilized plus charge. Just like in the benzene elimination mechanism, the phenylamine, the negative charge was also not delocalized. It was sitting in exactly the same orbital. So the only difference between the two is 2 electrons. And this is such a bad camper. It's generated surrounded, of course, this cation is surrounded by water in solvation shell. So as soon as it is being formed, it's trapped by water, and then proton comes off and you get the phenol. In fact, calculations show that there's not some argument whether it even forms or about the, some semantics about the lifetime of an intermediate. How short is short, and when is it so short that it no longer exists? Those kinds of arguments. But we'll write it as an intermediate like that, and you get the corresponding phenol. And so strategically, what you should think now is phenol is potentially derived from nitro arenes, and nitros, of course, are derived from the corresponding arenes, and all the rules of electrophilic aromatic substitution apply. Okay, so in a way, you can now think of OH as indeed introducible by electrophilic aromatic substitution by the sequence, with the same kind of strategic considerations of additional substituents and directing groups. Let's have a break. Okay, so that's methodology is clearly something that you should know and should be able to apply in synthesis. Another one